you want.
Yes.
We can't see the slide. Oh, we can see it now. It's working. Okay.
Okay. Thank you. Okay. Good morning, everyone. So, I am Shaktiranjan Mohanty from National Institute of Science, Education and Research, Bhubaneswar, India, working under the supervision of Professor Subhankar Vedanta. Thanks to the organizing committee for giving me the opportunity to present my work in this nice conference. So, first, the outline of my talk is I will first introduce briefly to my topic, and then motivation for carrying out this work, then the experimental techniques we have used, and then the results, and then summary and outlook. So, AtC-AtG interaction, as we know, it is mediated by conduction electron, and if there are suppose two magnetic impurity in a sea of conduction electron, then that two magnetic impurity can interact, and depending on the distance between the two impurities, and the coupling may be ferromagnetic or antiferromagnetic. And it shows a oscillating decaying nature that at certain thickness it shows ferromagnetic and antiferromagnetic, and certain thickness it shows antiferromagnetic, but the coupling decays gradually with increasing the thickness. So antiferromagnets, as we know, are really interesting because of their robustness against external perturbation, as well as they produce no stray field, and also they display ultra fast dynamics. But we are interested in synthetic antiferromagnets. So we should know that what are the advantages of synthetic antiferromagnets over normal antiferromagnets. That we can easily manipulate the antiferromagnetic order in synthetic antiferromagnet just by changing just by changing the thickness of this non-magnetic spacer layer. Other advantages, like we can detect easily by using the techniques which are used for ferromagnetic materials like squid VSM, magnetoptic, core microscope. That's why SF has advantages over normal antiferromagnets. And SFs are basically when two ferromagnetic layers are separated by a non-magnetic spacer, then both the ferromagnetic layer at certain thickness of this non-magnetic spacer become antiferromagnetically coupled. And here, by changing the, as I said, by changing the non-magnetic spacer layer thickness, we can tune it to ferromagnetic coupling as well as antiferromagnetic coupling. And then nowadays SFs are really interesting because of several properties. Like it can host scormion. Scormion, as we know, we can basically we can nucleate a scormion in a heavy metal ferromagnetic system, and these are very topologically protected particles to transfer the information in magnetic memory devices. But the disadvantage of scormion in ferromagnetic system is it shows scormion Hall effect. But if we use a synthetic antiferromagnetic structure, then in both the layers of this synthetic antiferromagnet, two scormions will be nucleated. And suppose the top scormion tries to move towards the right of the channel, then the bottom will try to move towards the left of the channel depending on its topology, because both the scormions are antiferromagnetically coupled. And ultimately, by the application of current, this coupled scormion will move in a straight line path in a nanotrack. So in this way, the scormion Hall effect will be reduced. So that's why nowadays SFs are really interesting. And also other interesting aspects of SFs are like it can be used in flexible spintronics also, which I will explain in my talk later. So for this work, we have used, we have prepared our sample in sputtering, especially as all our layers are metallic layers. So we have used DC sputtering. And for structural characterization, we have used cross-sectional TEM imaging. Then for magnetic characterization, we have used squid VSM available in our lab, and magnetoptic or effect microscopy, which is also available in our lab. So our sample structure is like on substrate, we have used a tantalum seed layer and then platinum in order to provide perpendicular magnetic anisotropy to this cobalt layer, then iridium as a spacer layer, then another cobalt layer in order to have this SAF structure like cobalt, iridium, cobalt, and then platinum to provide PMA to this cobalt layer as well as a capping layer. From the structural characterization by cross-sectional TM, we can see the layers have been grown very well and continuously. Even the ultra-thin cobalt layers are shows the continuous growth of the cobalt layer. And we have prepared several samples, like one reference sample we have prepared in order to confirm the perpendicular magnetic anisotropy in this thickness regime of cobalt. Then several samples having different combinations of this platinum cobalt multilayer, like below and above the iridium layer. And another sample we have prepared on a flexible polyimide substrate of 38 micron thickness, which shows SF properties and which shows also the change in interlayer exchange coupling by applying strain, which we will discuss later. So this sample, as I have mentioned my sample structure. So this sample is this plot is of squid VSM, which shows the antiferromagnetic coupling between the ferromagnetic layer at a thickness of iridium thickness of 1.5 nanometer. And in this sample, the below the iridium thickness, below the iridium layer, there are 2 platinum cobalt layer, and above iridium there is 1 cobalt platinum layer. So as you can see, this is the positive saturation, and all the spins are in up direction. And then while moving towards, while decreasing the field at fast reversal, one of the layer switches, and this becomes antiferromagnetically coupled. But again, reducing the magnetic field, the lower layer switches, but the coupling still exists, so that this coupling makes this upper layer again switch, and still from you can see from here to here, the regime is antiferromagnetic coupling regime. So in this regime, the sample is antiferromagnetically coupled, and again by increasing the field further, both the layers become negatively saturated with downward direction of spin. So in this way, we can explain this plot. And but this sample where the cobalt is below iridium and above iridium is 1 and 1, means 1 cobalt layer below the iridium layer and 1 cobalt layer above the iridium. This shows a 2-step reversal, where from positive saturation while going towards the negative, while going towards reducing the field, both the layers become antiferromagnetically coupled, and finally again reducing the field, both the layers become ferromagnetically coupled. And we have calculated the exchange coupling strength by this using this formula, JX equal to H exchange into MS into T, where H exchange is the exchange coupling field as shown in this plot, that where from here, if we further increase the field, both the layers become saturated, but before this field, both the layers are antiferromagnetically coupled. So we consider this field starting from origin to this point. We consider this field as exchange coupling field. Then MS is the saturation magnetization, and T is the thickness of the ferromagnetic layer. Then we have observed that by increasing the number of cobalt platinum layers, we have found the strength of the antiferromagnetic coupling is gradually increasing. And also we have calculated the anisotropy energy of all the layers by measuring the films in plane direction in squid VSM. And fortunately, we have observed that for all the SF coupled samples, means antiferromagnetically coupled samples, the anisotropy energy is higher than the interlayer exchange coupling energy, which means that there is a smaller intermediate angle between the magnetic moments of the 2 layers. Then we have also observed the magnetic domains by using magnetoptics core effect microscopy, and simultaneously we have taken the hysteresis loop, which shows the analogy with the squid VSM loops. And compared to the ferromagnetic domains, which we have not shown here, these antiferromagnetic domains shows very small. It shows very small domains in these antiferromagnetically coupled samples, and these 2 samples are with iridium thickness 1.5 nanometer, which are clearly antiferromagnetically coupled. But the samples with iridium thickness 2 nanometer, this loop shows a slanted reversal, where we have found very small ripple kind of domains, and this may be due to the canted type of reversal, means during reversal the spins may be canted. From this, we conclude that the spins may be canted. And then, in order to see the effect of stress on the anisotropy as well as exchange coupling energy, we have, as I explained earlier, we have prepared films on polyimide substrate of 38 micron thickness. And there we have considered the tantalum buffer layer thickness as 15 nanometer in order to reduce the roughness of the substrate. Before going to the exact details, I want to explain this magnet restriction. As we know, in a sample, if we apply magnetic field in certain direction and all the spins are aligned in the direction of applied magnetic field. So, especially in magnetic material, there we observe a change in length, but the length is very small, which we cannot physically measure directly, but the length is very small, and due to this change in anisotropy, and this is measured by a coefficient called coefficient of magnet restriction, lambda delta L by L. And from this, while we use it, while we mechanically apply a stress on this kind of flexible sample, we can see a change in its anisotropy as well as exchange coupling energy by applying mechanical strain to the sample. So in this sample, we have in our sample, in flexible sample, we have applied stress to the sample by mechanically bending, by putting it on a mold, and in this way, we have also calculated the percentage of strain we have applied, like compressive or tensile strain. From this equation, we can calculate the percentage of strain which we apply. T is the total thickness of the sample, including the substrate, and R is the radius of the curvature. And okay. So we have observed that in this sample, where the iridium thickness we have considered 1.5 nanometer, it shows clearly antiferromagnetic coupling. And upon applying of tensile strain, the loops, the exchange coupling field, it shows a little increase. As you can see, this is the unstrained condition where we have measured the sample in flat state, and upon applying tensile strain, the exchange coupling field increases slightly, and upon applying compressive stress, the exchange coupling field decreases. So we have also applied different value of strain, and we have observed similar behavior, like upon applying tensile stress, the exchange coupling field increases, and upon applying compressive strain, the exchange coupling field decreases. So it shows that SF shows a SF can be also used in flexible spintronics also. And in summary, we can say that we have prepared synthetic antiferromagnetic structures with where we have observed antiferromagnetic coupling among the ferromagnetic layers. Domain size becomes smaller on applying antiferromagnetically coupled samples, and also we can observe the change in coercive field anisotropy as well as exchange coupling field upon applying compressive strain as well as tensile strain, which will be advantageous for us. And further, we will try to nucleate skyrmions in synthetic antiferromagnets, and we will study its properties so that the skyrmion Hall effect will be reduced. I would like to thank all my co-authors, and I'd like to thank my supervisor, Professor Subhankar Vedanta, for giving me the opportunities to work in this field. And I'd like to thank all my lab members for their support and help in this work. Thank you.
Thank you very much, Shakti, for the great talk. We just quickly have some questions. What will be the impact if, instead of using a non-magnetic metal layer, we use an insulator? Do the two ferromagnetic layers interact?
If we use insulator instead of metallic layer, then what I know, that will not show this oscillating decaying nature. At certain thickness of this insulating layer, there may be antiferromagnetic coupling, but it will not show like antiferromagnetic, then ferromagnetic, then this will not show a oscillating decay nature. That the coupling will gradually decay. And this similar study has been already done in one of the work where they have used LCMO and CRTO. CRTO as insulating spacer and LCMO as ferromagnetic layer.
Okay, excellent. Thank you very much.